If your GPU is training in full precision everywhere, you may be leaving speed on the table. Torch.amp adds autocast and gradient scaling safely. You'll learn how the pieces fit into a workflow that launches mixed precision training and reports the speed gain. I'm Professor Pi, teaching AI foundations with simple Python. Mixed precision training fixes a real bottleneck. Big models move a lot of data and do huge numbers of multiply adds. If we use lower precision where it's safe, we cut memory traffic and speed up those heavy kernels. The win is a faster loop with similar final accuracy. Not a numeric mess. And torch.amp is popular because it fits PyTorch patterns and hides most of the bookkeeping. AutoCast lets the safe ops run in a lighter numeric format. And GradScaler keeps tiny gradients from vanishing. The trick is to keep reductions and sensitive ops in higher precision, while letting matrix multiplies shrink. That gets you float 16 speed math on supported GPUs, while keeping model quality where you expect it. We'll build a tiny training loop, then add AutoCast, a GradScaler, explicit unscale plus clipping, and run a few accelerated epochs so you can see the runtime and accuracy trade-offs. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let us start with a float32 baseline step, so we can measure the original cost before we change precision. This snippet establishes a float32 baseline training step on the tiny linear model. Without autocasting, every multiply add and model feature stays in float32, so the GPU or CPU handles more bandwidth than necessary for this easy dataset. The optimizer.zeroGrad, loss.backward, and optimizer.step trio shows the classic training rhythm we will augment later, so you can see exactly what torch.amp will replace. Features and labels stay on the same device, so there is no hidden transfer masking compute costs. The printed baseline loss shows the starting error that mixed precision training needs to match or beat. That baseline proves the model and loop are correct, but it still uses full precision everywhere. Next, we try AutoCast around the forward pass to see how D-types change and whether accuracy holds. This example wraps the forward and loss calculation in torch.amp.autocast, so eligible ops drop to lower precision. Running the same model features under AutoCast preserves accuracy because higher risk reductions and softmax pieces stay in float32, while matrix multiplies shrink to amp D-type. Keeping labels untouched lets cross-entropy see the identical targets, so any change you observe comes purely from precision choice. The printed AutoCast D-type confirms the tensor D-type actually switched, proving the context manager is active. AutoCast alone can make gradients tiny on some hardware. To keep training stable, we add GradScaler, which rescales the loss before backward, so gradients survive the reduced precision. This code bolts torch.amp.GradScaler onto the training step, so the mixed precision loss keeps gradients numerically healthy. Calling scaler.scale loss multiplies the loss before backward, letting tiny gradients survive amp D-type arithmetic, and scaler.step optimizer automatically unscales when it is safe to step. Because enabled toggles off when device is CPU, the same calls still fall back to plain float32 without branching your loop. The printed GradScale shows the current scaling factor that torch.amp manages behind the scenes. Scaling helps, but clipped gradient operations must run on the true gradient magnitudes. Next, we unscale explicitly before we clip, so the clip works as intended. This snippet unscales gradients before clipping, so safety checks still work after mixed precision scaling. Calling Scaler.unscale optimizer converts the parameters grads back to float32 magnitudes, which keeps torch.amp.utils clip grad norm about the real norm. That makes it easy to enforce max norm without breaking the scalar state. And the update calls remain exactly where they were in full precision. If you raise max norm, the clip lets bigger updates through. Lowering it tightens the cap, so clipped norm shrinks further. The printed clipped norm reports the capped gradient norm, showing the clamp kept the step within your stability budget. We now put the pieces in a short training loop to confirm the pattern holds across batches and epochs, and that quality stays high while runtime drops. This example runs a few optimizer steps with torch.amp still engaged to prove the workflow scales to a loop. The with torch.amp.autocast context stays inside the loop, so every batch reuses amp dtype, while scalar.scale loss keeps gradients robust each round. Both scalar.step optimizer and scalar.update sit at the end of the body just like before, so you do not need any extra conditionals to mix precision safely. Increasing the loop length trains longer for higher accuracy, while lowering it keeps the pass snappier but may underfit. The printed amp accuracy shows the trained model still hits the expected classification quality after the accelerated passes. This compact workflow transfers directly to a larger project. Swap in your real model, feed your dataset in the same loop, and reuse the same autocast and scalar calls. Measure wall clock per epoch and validation accuracy to decide whether mixed precision is worth it for your training. Mixed precision with torch.amp uses autocast to run safe ops in lower precision, and GradScaler to protect gradients. Use it when your training is bottlenecked by memory bandwidth or compute on a GPU that supports float16 math. One caveat: some custom ops aren't AMP friendly, so test numeric behavior before you deploy. Next step: run the same loop on a larger dataset and add simple timing and validation checks so you can quantify speed versus accuracy trade-offs. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.